arithmetic circuits. So this is the outline of chapter 5. We are going to see how to perform addition of binary numbers. We are going to see half adder and full adder circuit, two's complement system, two's complement arithmetic system, subtraction circuit, and the last part is addition and subtraction circuit. Okay, first part, 5.1, binary addition. Okay, binary addition is performed in the same way as decimal addition, except that the values of individual digits can only be 0 or 1. So the addition of a 1-bit number has 4 possible combinations as shown below. So in chapter 1, we have seen binary numbers. So but for binary numbers, we have only 0 and 1. Okay, so for binary addition, these are the possible combinations for addition process. So if we consider only 1-bit number, okay, it can be either 0 plus 0 or 0 plus 1, 1 plus 0 or 1 plus 1. Okay, so we are going to look at one by one. Okay, let's say 0 plus 0, the answer is 0. Okay, nothing is carry to the next bit. Okay, then if 0 plus 1, 1. Okay, nothing is carry. Then if 1 plus 0 also 1, carry equal to 0. And then the last one, if we consider 1 plus 1, 2. 2 in binary is 1, 0, right? Okay, 2 in binary is 0. Okay, try to recall back. Okay, why did I say 1 plus 1 equal to 1, 0? This is not 10, 1 plus 1 in binary equal to 1, 0. This is not 10. Okay, some of the students, they misunderstood as 10. Okay, 1 plus 1 equal to 2. So in binary, okay, recall back what have we learned in chapter 1. This is 2 to the power of 0, 2 to the power of 1. So the answer is 2. Okay, so that's why we have 1 plus 1 equal to 1, 0. Okay, so if you look at this, we have A plus B, we have S and C. S is the sum, C is the carry. Okay, next. When adding a larger number that has multiple bits, it is still necessary to add each pair of bits with a carry in. Okay, now we become, we go to the into more details. Okay, for example, we want to add A with the value of 13. Okay, 13 is expressed in binary as 1101. Okay, recall back the conversion that we have learned in chapter 1. 13 in decimal equal to 1101 in binary. Now we want to add 13 with 6. Okay, 6 decimal equal to 0110 in binary. Okay, so you arrange 1101 plus with 0110, and then you plus 1 by 1. So how you arrange? After you arrange, okay, try to see here. Starting from your right, the bit is known as A1, then followed by A2, A3, A4. As we move to the left, okay, the same goes for B, B1, B2, B3, B4. Okay, then when we add bit, the first bit for A with the first bit of B, we are going to get S1. Okay, then we are going to have C in that will be carried forward from here to the next part. Okay, then we are going to add C in plus with the second bit of A, second bit of B. Then we are going to get S2. Okay, sum 2. Then bring the C in to the next part. Okay, then C in will be added with the third bit of A, then third bit of B. Then we're going to get S3. And the process, then we're going to have next C in. Next C in also will be added with fourth bit of A, fourth bit of B. Then we're going to have S4. Then also we are going to have C in, and the C in will become C out if there is no more bit to be added. Okay, so now we try to apply the concept for the example A plus B, A equal to 13, B equal to 6. Okay, so we are going to add 1 plus 0, 1. Okay, nothing is carried to the next. Then, so we just put 0. 0 plus 0 plus 1 is 1. Nothing is carried, so just put 0. Plus 1 plus 1. Okay, 1 plus 1, 2. So 1, 0. So we have to carry the 1 to the next. Okay, then C in will be 1. 1 plus 1, 2. Okay, 2 equal to 1, 0. So 1 bring to the next. Okay, this one C in, the last one here will become C out. Okay, so the answer is 1, 0, 0, 1, 1. Okay, next we are going to see half adder and full adder circuit. Okay, when we want to add two bits A and B, okay, A plus B, we are going to generate two outputs, okay, S and C out, which is known as so the circuit is known as half adder operation. Okay, okay, so this is half adder. We represent it by using a square. Then we just write half adder. So the input is A and B. So output will be the sum and C out. Okay. So if we try to write the truth table for half adder circuit, okay, we consider only we want to add two bits only. Okay, 0 plus 0, sum is 0, nothing will be carried to the next. C out is 0. So 0 plus 1, sum 1, C out 0. 1 plus 0, sum 1, C out 0. 1 plus 1, sum 0 because 1 plus 1, 2. So 0 and then you have carry out 1. Okay, if you cannot get what I mean, okay, let's try to draw. Okay, let's try to write here. Okay, if you have okay 1 plus 1, so in binary you have the answer is 2. So this one is sum and this is known as C out. Okay, so that's how you have sum 0, C out 1. Okay, if we try to write the sum of product for the sum, okay, for the S, you will get A bar dot B. How to get A bar dot B? Okay, recall back what have we learned in chapter 3. To write an SOP, we have to consider the output 1. Okay, then check which row give you output 1. Okay, A0, B1. So A bar dot B plus with A dot B bar. Okay, then if you recall back from chapter 2, A bar dot B plus A dot B bar, this is actually the full expression for A XOR B. Okay, then for the next one, for C out, this SOP for C out, there is only one output, 1 here. Then you see how to get what are the combinations of variable here, A1, B1. So that's why C out the SOP A dot B. Okay, so that is the expression for half adder. Expression for sum and C out for half adder. Next, now if we consider 3 bits A plus B plus C in and generating S and C out, it is now known as full adder operation. Okay, why we have to consider 3 here? Because we are going to consider this scenario when we are adding large numbers. Okay, we are going to have C in here. Okay, okay, not only one output, only just one C out, but we are going to have many here. Okay, so this is the full adder circuit. Okay, you're going to add C in here. Okay, every time you want to add. Okay, you see from here, starting from the second column from your right, you're going to add with C in. Okay. Okay. If we do not consider C in, it is called half adder. But now if we consider C in, 3 inputs, it is called full adder. Okay. So basically, the diagram will be the same, just you have one more inputs here, which is C in. So that is the difference between half adder and full adder. Okay. So next, if you have 3 inputs, if you consider C in here, you are going to have 8 possible combinations. So A0, B0, okay. C in can be either 0 or 1. So the same thing when A0, B1, C in can be 0 or 1. So you have 2 possible input variation here. And then if you have A1, B0, also C in can be 0 or 1. So all total you are going to have 8 possible input combination. Okay. Then 0 plus 0 plus 0, of course you will have sum 0, C out 0, nothing will be carried forward. 0 plus 0 plus 1, the answer is the sum is 1, C out also 0. 0 plus 1 plus C in 0 also 1, C out 0. 0 plus 1 plus C in 1 equal to 2. Okay, so 2, the sum will be 0, C out will be carried to the next bit on your left. Okay, next 1 plus 0 plus 0, 1, carry out 0. Next A1, B0, C in 1. So you are going to have 2. So sum 0, carry 1, carry in 1, carry out 1. Then that carry out just now will be C in. So 1 plus 1, 2 also 0, S0, carry out 1. So this carry out from here will be C in for the next bit. So 1 plus 1 plus 1 equal to 3. 3 sum is 1, C out 1. Okay. So if you see from here, let's say 1 plus 0, the answer, the sum is 1. Carry out will be the C in for the next. And then 1 here, sum 0 here. Okay. So the C out from here will be C in for the next column. Okay. Okay. So next, if we try to derive the equation, the sum SOP, sum of product for sum and C out for full adder circuit, we are going to have this. Okay. Okay. So let's trace one by one. Okay. This one to have for sum, for full adder, we are going to have 4 output ones here. So A bar, B bar, C in, plus with A bar, B, C in. Then A, B bar, C in bar, plus with A, B, C in. And then you can apply Boolean algebra's theorem. Okay. and finally you will get this. Okay, you can try proof on your own this part. I'm not going to spend much time here. Okay, so finally from the equation, okay, for the sum you're going to have A XOR B XOR C in. Okay, so this is what we're going to have. AB XOR together and then XOR with C in. Then you have sum. Then for C out, we have C in dot with A XOR with B. Okay, XOR with B. Sorry, okay, just now AB. AB, we have AB. Okay, then XOR with is this correct or not? A dot B. Okay, then this one dot with C in. Yes, correct. Okay, then C out. Okay, so this is the full adder circuit. Okay, why full adder? Because we have three inputs A, B, and C in.